Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the awesome stuff. This is the AAS Journal Author Series. And I am super happy to have Marc Pound and Marc Wolfire with us today. Hello, Marc.
Hello, hello.
And Marc Wolfire, where are you located at?
In Maryland, at the University of Maryland.
Okay, College Park?
Yeah, College Park.
And Marc, you as well?
I am also at the University of Maryland, College Park, 2 doors down from the other Marc.
Okay, well, we should have put you guys in the same room or something when we were doing this one. So very cool.
About it.
Very cool. Let's see. Do we have any snow on the ground in Maryland on this January 30th? Nope, all melted, already all gone.
There never was any.
Wow,
they're predicting something tomorrow, maybe. We'll see.
Really?
Yeah, but it won't stick.
Interesting. So it is January 30th of 2023 as we record this, and I am in Phoenix, Arizona, and we're definitely in winter in Phoenix. We definitely got a little chilly this morning, a little bit below freezing, but it should warm up to a very reasonable 55 or so this afternoon. So very good. Nice. And Marc Pound, what do you like to do for research?
So I study the stuff that isn't stars. So things like this pillar that you see behind me. I'm interested in the interaction of gas and material around star-forming regions.
Cool. And Marc Wolfire, what do you like to do for research?
I mainly do theoretical modeling on these things, photodissociation regions that we will be talking about.
Indeed.
And so that's studying the interstellar medium in all different forms.
Nice.
The chemistry and the thermal processes.
Very nice. And that is going to bring us to this very lovely article. And I'm on this one. So the photodisintegration region toolbox, software and models for astrophysical analysis. And Marc, take us away.
Okay, so maybe Marc, I'll just give a short summary of what this is, and then you can talk about why we're doing it. So the photodissociation region toolbox, it's a Python package to study the regions that Marc and I and many others are both scientifically interested in, and that's the interface regions between H2 regions and molecular clouds, where a lot of interesting chemistry and physics goes on, and Marc will tell you more about that. And this package started life 20 years ago as a CGI bin script website, and we have kept it running all that time through many operating system changes and computer changes, with funding, without funding. And we finally convinced NASA to give us money to bring it into the modern age.
Nice.
And have written a full-fledged Python package with a lot more capabilities than the old CGI bin script was capable of. You know, it's gotten a lot of use in just the few years since we started development. It's being used on a JWST ERS program as a major component of that.
Cool.
And so we're very gratified that people are using it more and more, and we're getting lots of user queries about, can you add this? Can you tell me what's on here? And,
right.
So I'll let Marc now talk more about PDRs themselves, and then we can jump back to the code.
To the software instrument. Yep. Okay.
So PDR is a photodissociation region. I found over the years that it's hard to define what a PDR is without using the term region. So a photodissociation region is a region that is illuminated by stellar ultraviolet radiation, and that ultraviolet radiation affects the thermal processes and the chemistry in the gas.
Yes.
So it can photodissociate molecules to atoms, and it heats the gas mainly through
the grain photoelectric effect on small grains and molecules. So you think, well, these are pretty unusual or rare regions, but it turns out they're very, very common. So one place is where massive stars shine on molecular clouds. That's sort of a classical PDR, which was originally discussed in a paper by Thielens and Hollenbach.
Yeah.
But that UV can penetrate into the molecular cloud to an AV of a few. But there's also UV from the stellar radiation field on the other side of the cloud. So much of that GMC is actually in a PDR. It's still affected by the ultraviolet radiation.
Yes.
So we have GMCs that can be PDRs. The diffuse gas, all of the diffuse gas in the interstellar medium is in PDRs. There's reflection nebula, there's planetary nebula, there's protostellar disks, which are also in PDRs. And so it turns out that most of the non-stellar baryons in galaxies are in PDRs. So it's a lot of the mass. The interstellar medium is in PDRs.
Cool.
The PDRs also, since the UV radiation is absorbed by the dust and then re-radiated as infrared continuum, most of the continuum emission from galaxies is also in PDRs. So they're pretty important, we would say. So they emit then these infrared lines that can be used as diagnostics to understand the physical conditions in the PDRs. And that's what this tool does, takes advantage of.
Nice. Very cool. Very cool. Want to talk about the development philosophy?
Yeah, so I've spent much of my career developing astronomical software for end users, for observatories. I love writing software and I love writing code that helps people do science.
Yeah.
In addition to helping me do my own science. And so the approach that we took with this is that, it's open source, it's user-friendly. We're going to use, the packages that people are most comfortable with, AstroPy, Matplotlib, and we try to make the interface seem natural to kind of the modern age of astronomy, where people are used to things being AstroPy and being able to develop code in notebooks and things like that. And in fact, the package comes with a bunch of downloadable tutorial notebooks.
Very good.
On how to use it.
Very nice. Very nice. Very nice. Let me ask one question as long as we're here. What do you estimate is the size of the user base? Are we talking tens, hundreds, 10,000s?
I mean, right now it's probably maybe on the order of 100. It's hard to say. When we had this as a CGI bin script, we could track every a hook to the every call through general web analytics.
Right.
And so we knew where people were coming from, how often they were coming, what countries they were coming from. So we had people coming from over 35 countries for the old CGI bin script.
Okay.
With pip install, we don't know how often things are being downloaded.
Right.
You can get some metrics on that, but a lot of it is bots. But just from the sort of number of questions we get and knowing what our user base was before, there's probably, right now about 100 or so active users.
Cool.
But we're hoping that gets larger.
Grows, yes, understood. Yeah. Okay, very good. Thank you. Sorry, didn't mean to interrupt there. I just wanted
that's good.
Just curious. Let's talk about the PDR models inside the codes.
So I can talk about those. So those are the original PDR models were developed by Thielens and Hollenbach in 1985. And I have inherited their code, of course, with many updates and additions along the way. And there's several other groups that are also doing PDR codes that we've mentioned here. So basically what you do is you step into your cloud, you calculate the thermal equilibrium temperature, and you calculate the chemical equilibrium abundances.
Yes.
And you march through the cloud until there's no more PDR. And so when you're done, you have a temperature distribution and abundance distribution, and you know the emitted line intensities from all the dominant coolants.
Cool. Okay. I'm with you.
That's basically what it is. So I can put in a plug here for my annual review article. We have
Yes,
a
please.
2022 annual review article, which really goes into much more details on all of these points right there.
There we go. Go check it out. Very cool. Very cool. There we go. All right.
And just one of the things that we've done is that obviously Marc is a co-developer of this, so we want to highlight the Woolfire Kaufman code, but we've made this tool pluggable for anybody who has a PDR code. If they put their outputs in our format, it can go into it. And so we've done this now with the Cosmotau group in Germany. Now all their PDR models are in this package now too. And so you can choose which one you like, or see, they have different physical assumptions. You can see which one best matches your data. And so again, this goes to usability and getting the most science out. You want to give your users options.
Options are good. Options are good. Very cool. Very cool. And here's some of the example parameters in those models. They got abundances and capacities, velocities. Very cool.
Right.
And I think, here we go. Here's the PDR in detail, some of the models that Marc just mentioned that are in there. Cosmotau's, Wolfires. And I think we actually got this in figure 1. Let's talk about figure 1.
Yeah, so let's talk about figure 1. So figure 1 is a non-exhaustive table of the lines that we predict the intensities of through Marc's code.
Okay.
So that's on the left side, the species and the wavelength. And on the right side is what telescope those lines are accessible to.
Nice.
And you can see there's a number of NASA instruments there, which is one reason I'm sure why they chose to fund us. Sophia was a big component for studying, or a big instrument for studying PDRs.
Sure.
And it's kind of sad that it's not around anymore, but there's lots of good data in the archive that can be analyzed with this tool.
Nice. Good. Yes. Sophia.
And so we have the list of lines that are currently available, and then the list of lines that we're working on adding. And this is basically Marc, will calculate for a given line. He'll calculate the models for that line. We put them in the FITS format that we need for this tool, and then stick it online.
Cool. Very good. Very good. All right.
So I don't know, Marc, if you want to talk about any of these individual lines.
Well, I don't know. Maybe I think we should go on, perhaps.
Okay. And then we got a figure 2 over here, which is example of the model plots.
So this is kind of the fundamental format of what the model data look like. And so it's a prediction of, in this case, an intensity ratio. And this is the O1 145 micron intensity plus the carbon-2 158 intensity divided by the far infrared continuum. And Marc can jump in and say why that's an important quantity to be observed.
So the for in PDRs, the O1 lines, there's a 63 micron line and a 145 micron line, and the carbon-2 lines are the dominant coolants. So when you when you take a ratio like this with respect to the total infrared, you get some measure of the heating efficiency. So that's the energy that's converted from UV photons into gas heating. It's not quite that in this figure, because it would really need the 63 micron line as well.
Yeah.
But there's issues observationally now with the 63 micron line. I don't know if we need to go into that. Well, I should say that the 63 micron line is sometimes self-absorbed in regions, and so by foreground absorption. And so the 63 micron line emission that's emitted from the PDR can sometimes be absorbed by the foreground gas. And so the line that you observed is not quite all of the integrated line intensity that was emitted from the PDR. So, but the 145 micron line doesn't suffer from that absorption. So this is sometimes used as a diagnostic instead of the 63 micron line.
Got it. Cool.
I can also say that this is plotted as a function of the G0 versus density. So that is a measure of the incident ultraviolet radiation field.
Okay.
In what's called units of Hawking fields, where a Hawking field is a one measure of the interstellar radiation field. Okay. So a G0 of 1 here would be the interstellar radiation field.
Okay.
And you can get up to like 10 to the 5 for the PDR directly behind the trapezium.
Nice. Got it.
And then densities, there's a big range of densities there. These are constant density models. It's also possible to have constant pressure models, but these that we're showing here are constant density models.
Yep. Very cool.
And so that's one difference between the Wolfire Kaufman models, and what you see in the second panel is the Cosmetau model. They also allow non-constant densities, so they'll put a bunch of spheres or bunch of clumps in a volume and look at the radiation through that, and it's going to act differently than if it's going through a parallel plane. And so you can see these are two that were chosen to be sort of somewhat similar, but you can see they make different predictions for what the intensity ratio will be.
Wow, quite different actually. Yeah. Very good. Okay, I'm with you.
And so you can imagine as an observer, if you have a bunch of spectral, and actually we'll get to that probably in the next figure. So why don't we just go to the next figure?
Go there.
So let's let's actually go to the figure 4.
Okay, figure 4.
So this is, so you're the observer, and you've observed a bunch of different spectral lines, and you put your measurements into the tool, and it goes and says, okay, now what models do we have that will match your lines? Okay. So for instance, here's the observer puts in intensities of O163 and carbon 2 158, and a plot comes up of, okay, here's the theoretical model, which is log n versus now drain units of FUV field. Users can choose whatever units they want. Drain is another version that people like to use instead of Hawking, but they're pretty close. And so the value of their observation with the error bars is that green trace through the middle.
Yes.
And then you can go over the middle panel is another set of lines, carbon 1609 and CO 43. And again, it crosses some other place in that density flux plane. You can see where we're going with this, right? And the next one is the difference that crosses another way in that same flux plane. And so now you can think about, okay, if we laid all those on top of each other,
right?
Where's the point in space where they all cross? And I think that's the next figure.
Okay. See that. Figure 5. Oh, so they are. Here we go.
Right. So now here's, so all these observations give you a region of this theoretical space
Cool.
where all the observations match. Well, this is, you know, a nice, well-chosen, well-behaved case. It's not always this well-behaved. But this, so the user can visualize this, and they can also do chi-squared fitting and that, you know, find the actual value with errors, or they can do Bayesian fitting with the MC package, which is built in, which you can see in figure 6 there.
Right.
So this is yeah. So you get a corner plot, or if you scroll down a bit, you see what the chi-squared plot for that particular thing would be.
Very nice.
And this is all, you know, simple little function calls in the interface to get these plots out. And I do want to say that every plot that you will see in this paper was made with the toolbox. So we strive to make publication quality figures from the outset.
Right.
And in fact, what's in the appendix is the code listings that not only demonstrate the code, but make all these figures.
And I have to show that just because it's relatively unusual these days. This goes back a few years when people would do this, but I think this is really lovely to be able to lay it out like this. Very clear.
And it was actually a bit of a struggle with the journal editing process to get these to show up right. It's still a work in progress, but they were very helpful in the end.
Yeah.
And all this code is downloadable.
It's on GitHub
with our package. It's on GitHub.
Yep.
And it's also part of our integration testing, so that code will always work.
Nice. Very good. Very cool. Okay. So some of our plots and
so what we showed you in the last thing was just a single beam or single pixel observation.
Right.
Right. But you can do this at every point in a map. And that's what the next figure shows. So these are some data from a paper by Katie Jameson and collaborators from 2018.
Okay.
So they observed a bunch of these lines in continuum in a star forming region in the Small Magellanic Cloud.
N22.
And back then we didn't have this nice package, and the way they made the maps for their paper was they did a call on the CGI bin script for every map.
One. Oh wow. Okay.
You know,
wow.
and n times and then put it together in a map. Now you know, doing this with the Python package takes
boom boom boom
like 90 seconds or something like that. For this is about 5,000 pixels.
Cool.
And then you get maps of the density and the radiation field.
Cool.
And this was with, I'll give another plug for Marc's models. The SMC has a lower metallicity than the Milky Way. And so we have a whole set of models just for the metallicity of the SMC.
Great. Very nice. Certainly beats calling a CGI script 5,000 times.
Yeah.
Indeed. Cool. And then we have an actual example of a fit. All right. Great.
Okay. So Marc, do you want to talk a little bit about excitation diagrams,
Yes.
general and H2?
Yeah. So this is really basic observational analysis. This is not a model. This is just taking your data directly and making excitation diagrams. So this is for H2. So you can convert the line intensities to a column density. So on the left side, you take the column density divided by the statistical weight, and on the bottom is the energy of the height above ground for that transition.
Okay.
And for H2, this is a typical excitation diagram that you get from a PDR, and you can see there's two different slopes. The lower one comes from the lowest. This is for purely rotational transitions, but Marc has modified this to make the vibrational diagrams as well.
Okay.
But for the lowest rotational lines, that line through those column densities gives an estimate of the gas kinetic temperature.
Yes. Okay.
For the J equals 2, J equals 3 fit, that gives a measure of the kinetic temperature. And for the upper levels are pumped by this UV fluorescent process. So that gives another measure of temperature. It's not really the kinetic temperature, but it tells you something about the excitation of those levels due to fluorescent pumping.
Okay.
But Marc's a tool here does all of this automatically.
Boom, boom.
You put in the line intensities, and you get the fit to the cold component, the fit to the temperature to the upper lines, and it also gives you an estimate of the ortho to para ratio by finding out what shift is required to give you a straight line through those points. And you also get column densities from it.
Cool.
And
Nice.
so, well, maybe Marc can talk about how we did this script.
Magic.
Lovely. Great magic.
Yeah, I mean the way it does it is that it takes the lower rotational line, so that the J equals 2, 3, and 4, and makes a guess at what the initial cold temperature might be, and it takes the other ones and makes a guess at the initial hot temperature, and there's a little bit of magic to figure out where that split should be, and then it can do a fit. And then the ortho to para ratio, it's just a matter of so the ortho to para ratio can change for the odd J lines, and so you can and the canonical value is 3, but if you often see this sort of zigzag in the data, and if moving every other point up on the y-axis can give a better fit, and they're all consistent with each other, in this case an ortho to para ratio of 1.86, then that tells you something about the conditions in the cloud, and it's an allowable fit. And so the tool sort of messes with all these things. As long as you have enough points, it can do a fit. And again, this is for a single point. We didn't show this in the paper, but it's in the notebooks. You can do this for every single point in a map, and you can get an excitation diagram for every single point in the map. You can get maps of the temperatures. You can get maps of the ortho to para ratio. You can get maps of the column density.
Cool. Very useful. Very useful. That is nice. Very nice. Okay. Diagnostics, PDRT.
So maybe, Marc, you want to talk about diagnostic diagrams, and this is for the ionized.
Yeah, so this is for the ionized gas. So again, these are not complete H2 region models. This is using excitation diagrams that I generated using Chianti, which is a program for ionized gas. And so you're basically just taking the ratio of emissivities here. And we picked iron 2 because of JWST should see a lot of the iron 2 lines. And so by combining different lines, in this case, we have the 1.60 over 1.64 micron line ratio, and that turns out to be a good measure of electron density. And then we have 1.64 over 5.34 micron ratio, and that turns out to be a good measure of electron temperature.
Yes, good. Okay.
And so we combine these. It's kind of a ratio plot. So by plotting observations on there, you can determine simultaneously the temperature and the density.
Right. Which is always a good thing to have. Very good. Helmholtz free energy and all. Very good.
And so maybe what I'll say is that this sort of what we call a face-based plot, where basically you're plotting the observables on the axis, and it's the models that are within the frame, if you will. That's a generic tool in the toolbox. And so if you scroll back up to figure 3.
Yes, let's do that. Figure 3.
This is the exact same code,
yeah.
but instead it's showing the submillimeter lines ratios on the x-axis, and Marc's PDR models, the G naught and N values, the G naught and N grid in the frame with data on top of it. And so
I'm with you.
it's a reusable tool in many ways, depending on what you want to use it for. But it's basically to sort of flip the way that you think about your data, right? Think about your data in the grid of the model space, rather than the model space in the frame of the data.
Right.
And then these are all actual data from a star forming region, from Tavari et al.'s paper.
Cool. CW49. Very nice. And I think last but not least, we have figure 10. There we go. When do we get in trouble?
Right. So, it's important to be honest about what your code does and what its problems are, because as we know, codes evolve, right?
They do.
So, the first example we showed you of what we call the overlay diagram, sometimes colloquially known as the spaghetti plot, all the lines crossed in one spot, right?
Concordance, yes.
But real life can sometimes be more difficult. And this is an example where there's two, more or less equally valid solutions to the data. One is a high density, low radiation field solution. And the other is a low density, high radiation field solution. So what's the hapless observer supposed to do? And if you just do fitting sort of pixel by pixel,
okay,
it's an ill-conditioned problem. And so you can get what happens in the middle panel, that adjacent pixels flip between these two solutions, depending on exactly what the signal to noise is on that particular value, right?
Fair enough.
And so you get a nonsensical answer.
Right.
And so this is an example of the code does something wrong. And if you look at the actual observations, which is below, it's a smooth, the observations are smooth. So, so the solution for G naught and N should also be smooth. And so this is not an uncommon thing to happen in these sort of inverse problem codes.
Yes.
And the way to solve it is a technique called regularization, where you bring in some additional information to constrain the solution to the problem. You can think of it as adding a penalty term. I think we have if you go to equation 2, actually.
Equation 2.
Which is just below the figure.
How did I miss that? Oh, there we go.
The normal thing that people do is a chi-square solution, right? Which is that first term, right? But if in this particular case, if you just do a chi-square solution, you bounce between two different things. So you add a term that says, for instance, the solution has to be smooth on the same spatial scale that the data are smooth, right? You think about some mathematical way to capture that.
Okay.
Or some other way of constraining the data.
Yes.
And you can add that term, and it should help solve your problem. So this is something, it's not in the code now. We want to add it to the code as kind of the next big development that we want to do in the code. There's kind of many ways to do regularization. I'm not an expert in it, so I'm still learning about it too, and talking to people who have done this sort of thing. But that will make the tool much more useful for these cases where you might get into trouble. I mean, the real thing we would like to tell people is, well, just go get another observation, and that will break the tie. But that's not always possible.
Right? Not always going to happen.
Yeah.
Cool. Very nice. Very nice. All right. Well, Marc squared. Thank you so much for walking us through your very lovely article on this new rendition, modern era of the photo disintegration region toolbox. Very cool. So let me ask, since you touched on it a couple times, where do we go from here over the next couple of years? As anyone who writes software knows, but by the time the actual article comes out, it's behind the software. So is there going to be a paper 2 on this particular version? What's the time scale for getting those additional lines in, and just general future of this toolbox over the next couple of years?
We do kind of outline in the paper. You don't have to bring it back up. That there's sort of 2 categories of improvements we want to make. There's improvements to kind of the Python code, so like the regularization that I talked about, and other things that maybe users have asked for. And then there's improvements to Marc's models that will also improve the science. And so maybe, Marc, you want to talk more about the improvements to the PDR code, and then I can talk about the other part.
Well, typically we get requests for different metallicities, in particular much lower metallicities.
Yeah.
These are really designed for local galactic conditions. And we have some for the LMC, but we really want to make one for the SMC as well. One problem with the SMC is it has very different dust properties as well, so that can change the extinction curve, or column densities and things. And so, but those are things that we can put in, and make a uniform set of models that would be applicable to the SMC.
Okay.
But lower metallicities and
viewing angles.
Oh, viewing angles, yeah. So originally these were for face-on PDRs, but in one of a paper by Cornelia Pabst, we tried to put in a model for directly edge-on. So we adapted the models to do them for very edge-on, but we want to try to make that a little more flexible and see if we can provide models for various viewing angles.
Okay, nice. What is sort of the release schedule of new releases? Do you happen to do one organized release a year and you give it some name, or is it sort of as it happens? And
it's kind of as it happens.
Okay.
It seems like we're doing about 3 to 4 a year.
Okay.
In fact, I'm going to hold my feet to the fire, and there should be another one in about a week.
Okay. We'll go get them.
JWST proposals delayed that somewhat. But it's really kind of as things accumulate, or if there's, a new set of models that we want, like we just got a whole new set of Cosmetau models.
Ooh, okay.
So I want to get those out and get those into the community, right? So I can do a release that's not really any code changes, but is just models. So it really depends on what users report they want. A number of our tools, like that FaceBased tool, that was driven by a user or a user group. So the Sophia feedback team wanted those kind of plots. So we said, okay, let's get those in, right? And so something that's very useful like that for the whole community, that could drive a release.
Okay. Okay.
And I mean, I'm, the main developer, so it's kind of on my schedule. We welcome open source development. Please come and write code for us.
Go do it.
And in fact, we do actually have someone, so that H2 molecular hydrogen excitation tool, it's fairly generic, and someone has written a version of it that can do the carbon monoxide
Ooh.
infrared line.
Okay.
And we want to get their
Mm-hmm.
code from them. They didn't really fork the GitHub. They just sort of like hacked it. So we want to get the code from it, get that into a release.
Right. Excellent. Super. Sounds like a good plan forward. Well, I really look forward to seeing both the models and the source code and just the general project move forward over the next couple of years, and makes even more useful and valuable science-wise to the users. It's great. And we'll learn something a little bit about photodisintegration regions while we're at it. So what a deal. What a deal. All righty, Mark. And Marc, I want to thank you so much again for walking us through your very lovely article and Toolbox. So thank you very much.
Thank you so much, Frank.
Thanks. Thanks a lot.
And that'll do, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.
Bye.